I will begin with a word of prayer. Ahem. Hem. 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 So, Father, we thank you for this day. And Lord, I thank you for these students. Just ask you to bless this class, Lord. In your name I pray. Amen. Welcome to the visitors. Yes. My apologies if this doesn't make a lot of sense. But the good news for you is that the students are also lost. So, lots of good company. I'm just kidding. They understand everything I say. All right. So last time we were talking about matrix groups, which are perhaps not surprisingly groups formed by matrices. And essentially, I gave you examples where G was a subgroup of G, L, let's say N, K, with the K either equal to the reals or the complexes, right? Those are the examples I stated. We looked at about a dozen examples. What I failed to say last time is perhaps we should add the condition that G is a matrix group. We need something else, actually, beyond just that it's a group. It's usually assumed that G is closed. This should be closed in the topological sense. So what that means is the following. If you have a sequence, say A sub n in G, all right, then the limit as n goes to infinity of A sub n is also in G. So a sequence of matrices which converges in the group must converge to a matrix in the group. This is a way you could describe the group being topologically closed. All right. That's just a bit of minutia. It doesn't really have much to do with what we're doing today. So I posed the question of looking at these matrix groups and trying to calculate their dimension, right? We calculated the dimension of SL2 was 3 last time, right? And let's do another example just to get started here. How about this? If we look at O2, that's going to be what? We got A, B, C, D, such that what? A transpose A equals to the identity. So this is a subgroup of what? This is a subgroup of GL2R, right? And we decided last time that this is 4 real dimensional, right? So my question is, if you think of O2 as a space, you know, what kind of space is it? Is it a one-dimensional space? Is it a two-dimensional space? Is it a three-dimensional space? You know, what is it? Well, you know, the first and sort of most naive way to think about this is just to think about the equations which define it, right? So what equations define it here? A transpose A equals to I. So my question to you is, how many independent real equations do we have here? What is A transpose A equals to I? It's a 2 by 2 matrix equation, right? So we could have as many as 4 independent real equations. But how many independent equations do we actually have there? How many? 2? So I have a vote for 2. Let's work it out. A, B, C, D times the transpose of that, which would be A, C, B, D, right? Multiply this thing out. What do we got? We got A squared plus C squared. And let's see here, BA plus DC. And we've got, what do we got up there? AB plus CD, right? And then down in the 2 component, we got B squared plus D squared. This is all equal to what? 1, 0, 0, 1. So how many independent real equations do we have? I think that the diagonal equations are independent, so we have at least two, but there's a third equation, right? The off-diagonal. But you see the 1, 2 and the 2, 1 equations are really the same equation, right? So after you do all this, I think it's pretty clear that the answer to that is 3 real equations, right? So what's the dimension of the space? So the dimension of O2 as a real manifold is 4 minus 3, which is 1. So O2 is a one-dimensional Lie group. This is just like, remember, you guys have had calculus 3. We checked last time, right? So in calculus 3, we talk about a level surface. How does that work? We have what? F of x, y, z equals to a constant. What is that? That's the solution set. What have I done?
Can you just explain why 1 is not 3?
Because the number of equations reduce the number of degrees of freedom. It's just like this. So a level surface, we have one equation in 3 variables, right? Like what's the dimension of this? If we have x squared plus y squared plus z squared equals to k, suppose k is r squared, you might recognize that as a sphere of radius r, right? It's the ambient dimension minus the number of independent conditions that gives us the dimension. So we have to, like, we're in a 4-dimensional context. We've got 3 independent conditions. That leaves us with 1 degree of freedom. That's why it's one-dimensional. Now you could take a parametric viewpoint, right? Oh, what if I looked at SO2? SO2 would be what? A in O2 such that what? The determinant of A equals to 1. Yeah? What's the dimension of SO2? You know, if you're really sloppy in your thinking, you might be tempted to say the dimension of SO2 is 0 because we already were in a one-dimensional context. I added another equation, but that's not the case, right? Because what does A transpose A already tell you? The determinant of A squared, right, is equal to 1. So the determinant of A is plus or minus 1 for an O2 matrix, right, for an orthogonal matrix. So that doesn't really reduce the dimension. This determinant 1 condition doesn't reduce dimension at all, does it, in this case? It did last class because it was the only thing we had. We were looking at SL2. We looked at the determinant equal to 1. But the thing is, the context there, we hadn't already imposed that condition by other things we'd said. So yes, SO2 is also one-dimensional, right? And I can do better here. I can show you the parameterization. SO2, what does it look like? It looks like this. It's cosine theta minus sine theta, cosine theta, such that theta is an element of 0 to 2 pi. That's a parameterization, if you will, of the special orthogonal group. And so there, it becomes manifestly clear why it's one-dimensional, because it's described by one parameter. And this is the idea we saw in calculus 3, right? A one-dimensional manifold is a curve. It has one parameter. A two-dimensional manifold is a surface. It has 2 parameters. And we could have talked about space being parameterized. That would have 3 parameters. We actually did that with coordinate systems, right? Polar or spherical, cylindrical or spherical coordinate systems. We needed 3 parameters to describe a point in 3-dimensional space. So the question, the thing that you're getting confused about is the distinction between equations which define the space versus parameters which define the space. And these are complementary ideas. Oh, I did take attendance today. Cool. All right, good. Now, but anyway, I think this particular viewpoint is going to get really kind of a pain if we go on and do more complicated examples. I mean, I can afford to do one more example in this style. If we look at O3, right? So there you're looking at A in R3 by 3 such that A transpose A equals to the identity. That's A transpose A equals to the identity here. It's nine possibly independent equations. How many independent equations do you actually have here? GL3R is a 9-dimensional space in terms of real manifold dimension. Well, if you look at A transpose A equals to I, again, it's the same thing we just saw over here. Like the lower diagonal equations and the upper diagonal equations are just going to be, they're going to be the same when you go through the details. Basically, the equations are invariant under transposition is the thing. The equations are in some sense symmetric. So there's really just six independent equations here. So the dimension of O3, the theta 3, listen to me. The dimension of the orthogonal group, size 3, is going to be 9 minus 6, which is 3. So in fact, this is a 3-dimensional Lie group. Likewise, SO3 would be 3-dimensional. Right? All right, so this way of thinking is it's not a bad starting point, but if you try to do something like calculate the dimension of, I don't know, something like SU2, right? What was SU2? Remember this guy was A in C 2 by 2 complex matrix, such that what? A dagger A equals to the identity, where A dagger, we said, was a conjugate transpose, the Hermitian adjoint. And I tell you, if you try to sort through how many independent equations there are, it gets really kind of hairy because we've got 4 complex equations, but they're somewhat redundant, and like actually thinking through it, I found to be rather cumbersome. So I like to take a different viewpoint if I'm going to try to calculate the dimensions of more interesting groups than the ones we've done so far. A useful tool for thinking about that is given to us by the larger problem of manifold theory. So let me just say a word or two about manifold theory. What is a manifold? It's simply this. It's something like some kind of abstract space. All right? You could have holes in it, whatever. But the thing is, with a manifold M, if you zoom in on any point, all right, like some point P, there's something called a chart, X, and that chart will get you to Rn. So in n-dimensional manifold, there exist these coordinate charts that give you a one-to-one map between the manifold and Rn, but not the whole manifold necessarily. So the reason it's called a chart, it's a, much like we talk about an atlas. So you can, around some open set around the point, you get some sort of bijection between some neighborhood of the point and some subset of Rn. All right. So this X is a one-to-one map, which maps a neighborhood of the manifold to Rn. And you can go back and forth. It's an invertible map. And if you study manifold theory, we use the coordinate charts to define calculus on the manifold. Basically, you just take calculus down here in Rn and you lift it up to the manifold in a systematic way. Obviously, we're not going to do that in here, but just to give you a sense of what I mean by manifold. It's an abstract set which has an atlas, which means it's got charts which cover the whole thing, and at any point there's a one-to-one correspondence between an open subset of Rn and the manifold. In this case, the dimension of the manifold is the dimension of the local modeling space, which is Rn. So the dimension of the manifold is just equal to n. And that's the thing about a manifold, is it has the same dimension at each point. All right. If I tried to take like a surface and glue a tail on it, that wouldn't be a manifold, because it's got one part that would be two-dimensional, but it's got another part that would be one-dimensional. That's not allowed. Manifold has to have equal dimension over the same thing. But the other neat thing about a manifold is the concept of tangent space that we talked about in Calculus 3 also generalizes. So you can look at all possible curves that go through a point on the manifold, and in some sort of natural way, you look at all possible curves that go through the point like that, and you can in some sense think geometrically about there being some sort of tangent space at the point to the manifold. Now, we don't actually think about it literally being on the manifold. It's a separate abstract object, this tangent space. But the tangent space to the manifold also has n dimensions. So a nice way to calculate the dimension to the manifold is to calculate the dimension of the tangent space to the manifold is also equal to n. And the reason I say it's easier to calculate the dimension to the tangent space is because the tangent space to the manifold is really just this. Its equivalence classes. Oh, let me not be too technical. All right, let me lie a little. Okay. Small bit of dishonesty. So it's tangent vectors where gamma is a mapping from the reals to the manifold. And let's suppose that gamma of 0 is the point. So it's the set of all possible tangents to the point. That's what the tangent space is. This is actually pretty easy to calculate for matrix groups. So, definition, the tangent space to the identity for a matrix group is defined to be frac G. So frac G, in other words, gamma prime of 0, such that gamma is a mapping from the reals into G, and gamma of 0 is equal to the identity matrix. This is the tangent space to the identity matrix of the group. All right. Now, the reason for this symbol, frac G, is that this is also, it has additional structure. If we study this further, we won't do this too much today, but just a little bit. This actually has the structure of what's called a Lie algebra. So the frac G, this thing here, is actually the Lie algebra of G. Lie algebra is a much more concrete object for you guys. It's a vector space. All right? So that means we have all of linear algebra to bear on that. It's pretty nice. So let's actually calculate the tangent space at the identity for, I don't know. Well, let's start out with O3 since we already have our pause on that one, yeah? So O3, let's see here. Consider gamma from the reals to O3 such that gamma of 0 is equal to the identity. So what condition do we have on this path? So the condition on the path is this: gamma of t transpose times gamma of t is equal to what? What does it mean to say gamma goes from R to O3? That means gamma of t is an element of what? It is like the A, right. What I was fishing for here was something that comes before that, which is that gamma of t is itself in O3, right? Which means it's like the A, which means that this has to be equal to I, right, just like that. Gamma of t is like the A over there, perfect. And so we can do calculus on matrices. You may recall from linear algebra that we can differentiate a matrix of functions, and it has a product rule. So the product rule is simply this: gamma prime of t transpose times gamma of t plus gamma of t transpose gamma prime of t equals to, I'll write this one out in differential notation, d dt of the identity. How does the identity matrix change with time? This one's easy, Liam. Go for this one.
I'm sorry, I'm still writing down what you wrote.
When I ask this question, your answers are 0 and 1. You got 50-50. They're not your friends. It's 0. It's 0. Yeah. So, yes. So the identity matrix is a constant matrix. The derivative of a constant matrix with respect to time is 0. Yes. Now, I don't know about you. So this identity is true for all time, right? For all time. But really, it's most fun to look at this in the case, let's let gamma of 0 equal to b. Actually, let's let gamma prime of 0 be equal to b, because gamma of 0 is already what? The identity, right? Yeah. So what do we got? We have b transpose times the identity plus the identity transpose times b equals to 0. What is that? This gives us b transpose equals to minus b. That ain't bad. That's just skew symmetric, right? So in other words, the Lie algebra, which is also denoted little o3 versus o3, if you can see in the same font, okay, is just equal to b in our 3 by 3 such that b transpose is equal to minus b. You have seen this in homeworks before. The dimension of antisymmetric 3 by 3 matrices is 3. Right? Zeros down the diagonals and the off diagonals fix above or below the other side. Which of course is the same conclusion we came to here with my dark magic equation counting, right? Yeah. Now, we can do better. We can do better. To do better is to introduce the matrix exponential. You remember the matrix exponential, right? What is the matrix exponential? Well, glad you asked. Let's see here. Theorem, exp, we can define as a mapping from the Lie algebra of G to G by, and we had a more sweeping definition that I gave you in linear, and you could go back to that. This is just the restriction of that for my current purposes, but sum n equals 0 to infinity of b to the n over n factorial. I mean, that's a formula for it. Great. You can show that the derivative with respect to time of e to the tb is equal to b e to the tb. So gamma of t equals e to the tb has two nice features. One of them is that gamma of 0 is equal to e to the, well, 0. By the way, this looks like I plus b plus 1/2 b squared plus da 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 da. And if I was to put a t up in there, which would be convenient for my current purposes, what happens when we put t equal to 0? we just left with, so that's good. The matrix exponential, when you evaluate it at 0, gives you back the identity matrix. That's comforting. But also, what's gamma prime? Gamma prime of 0 is, in fact, B. So a nicer way to look at a path through the identity of a matrix group is to look at it in terms of the matrix exponential. All right. In fact, we have a theorem, which is this. If we let H equal to e to the TB, such that T is in the reals, then that's a subgroup of G, provided that B is an element of the Lie algebra. This is also known as a one-parameter subgroup of the matrix group. Every thing in the Lie algebra generates one of these things. Now, there's more. There's more. I should mention, if we take e to the ta times e to the tb, right, then it works out to e to the ta plus b plus, oh, unfortunate, my choice of, let me drop the t's here if you guys don't mind. Otherwise, I'm gonna go nuts. A, B, e to the a times e to the b. I'd actually have to think about the t's. That's a plus b plus 1/2 ab. And then an infinite series of things, actually. It's like 1/12, well, plus or minus 1/12, a with ab, plus or minus, I forget which is, it's not plus or minus because it's actually plus or minus. It's plus or minus because I forget which one comes first, okay? So that's not the kind of plus or minus we typically see in math. That's a plus or minus brought forth by ignorance of the instructor. My apologies. But my larger point is that the higher terms in this are all nested commutators. Here, this notation, AB is equal to AB minus BA, the so-called commutator of A and B. So in the case that AB is equal to, the commutator of A and B is 0, we get what? Well, let's say M and N. If the commutator of M and N is equal to 0, then e to the m times e to the n is equal to e to the m plus n. And that's it. But when they don't commute, you've got to take account for all these higher commutators. That's what informs the group law. But what you have here is really something pretty beautiful. On the left-hand side, I have what? I have a multiplication in the group. On the right-hand side, I have a series of things formed in the algebra, the Lie algebra. And this is this formula is why we say you can exponentiate the Lie algebra to form the Lie group. That's not actually quite true. It's only true if the Lie group happens to be connected. Right? Let me not get too technical there. All right, so we could, well, let's work out one of these. Let's try this out on SU2. See how that goes. All right. Well, fine. Sorry. It's not ideal, but it had to happen. All right, so example. If we look at U2, all right, which again was A in C2 by 2, such that A dagger A equals to I. If we have B in the Lie algebra of U2, which you might use a little u2 for. This is the typical notation is like this, guys, GL2R. Then you have like GL2R. This is the group. This is the corresponding Lie algebra. This is a notational scheme. We use lowercase of the same notation to denote the algebra, uppercase for the group. That's a pretty popular notational scheme. Anyway, suppose B is in the Lie algebra to this, and let's look at gamma of t equals to e to the tb, right? So I would have e to the tb conjugate transpose times e to the tb equal to the identity, right? So you differentiate this, what's it tell us? By the way, you can prove that that's e to the tb conjugate transpose. That's a property of the matrix exponential. The conjugate transpose of the exponential is the exponential of the conjugate transpose as it happens. So we have that. That's just linear algebra, really. Differentiate this, what do we get? And set t equals to 0, what do we find? B dagger plus b is equal to 0. Because e to the 0 is y. So what we've just found is that the Lie algebra for U2 is apparently formed by skew Hermitian matrices. If I can work it in here somewhere. So this is B in complex 2 by 2 matrices such that B dagger equals to minus B. Now, what's the real dimension of that? I don't think it's quite obvious yet, right? Let's actually write out some letters and see if we can work through it. So let's let the matrix have components A, B, C, D. Yeah. So we've got A, B, C, D with a minus on it equal to what? A conjugate, D conjugate. But we flip the off diagonals, right? B conjugate, C conjugate. That's the Hermitian. So what are the conditions we find? You've got A bar equals to minus A. You've got D bar equals to minus D. And you've got C bar equals to what? Minus B. Is the other, so I saw that third equation, I saw that from looking at this and that. If we look at this one versus that one, is that anything new? That's minus C is equal to B bar. That's the same third condition, right? So we really just have these three independent equations. What do they say? Remember, A, B, C, D here are generally complex. What does that say? If it's equal, if they're equal to, well, let me just go ahead and tell you. This means that B can be written as something like, I don't know, let's say I theta, I beta, minus I beta, I gamma, where theta, beta, and gamma are real numbers. So it's I times something of the form theta, beta, minus beta, gamma. Here I'm saying theta, beta, and gamma real. So it turns out that the Lie algebra of U2 is also 3 real dimensional, because we have 3 real parameters in the answer in a typical matrix in the Lie algebra. All right. So here's what's more is you could actually prove that if you look at this, so if you study the way the brackets work here, right? So it's three real dimensional. You could find a basis. You could find a basis for the frac G. You could write frac G as the span of F1, F2, and F3, where those are particular skew Hermitian matrices. And you could show that with respect to that choice, if you look at the commutator, Fi and Fj would work out to, I believe it's epsilon ijk, where that's the Levi-Civita symbol, the thing that's 1 if I, j, and k are 1, 2, 3. It's -1 if you switch them, and it's not important actually, the details. The point is that you could show the commutator works out to that for a particular choice of basis, and you could actually do the same thing for SO3. All right, SO3, in fact, or O3 for that matter, they actually, you could also choose a basis for these guys, let's say GI and GJ, and you could show that the commutator of those is in fact given by the same. All right, I think I lost a very important F sub k here. So these two groups have in fact the same Lie algebra, because by the way, the commutator bracket tells you the structure of the Lie algebra. And you might ask the question, so we have two three-dimensional groups, right? Two three-dimensional groups, and they have the same Lie algebra. Do they have the same, are they isomorphic? What do you guys think? Is it the case that if we have tangent spaces which match up, and if we study the commutator bracket on the tangent spaces, is that going to be enough to give us that the groups are isomorphic? The answer is no. Let me just take a minute or two to show you why. Actually, it's going to take me about 10 minutes, so that's fine. I'm just happy my email loaded because it wasn't at the start of class. So at this point, I'm going to share with you guys some really interesting results from Christopher Tapp's Matrix Groups for Undergraduate book, which I mentioned last time, right? And eventually it will work. What do you guys want, blue or green? Blue or green? Getting very mixed messages here. I'm going to start with blue. I said purple. All right, so So I will, by the way, I'm going to post this PDF in course content, so you don't feel obligated to write these things down, all right? I don't think you could if you wanted to. All right, so here are some results of interest. In particular, if we have G is one of these guys, SON, UN, SUN, or the symplectic N groups, then in fact, every element of G can be formed by the exponential of something in the Lie algebra. So in fact, it can be proved that the exponential is surjective onto these particular matrix groups. And that is partly in hand with the fact that G, all of these example groups are path connected. What does it mean to be path connected? This is really, really complicated, so pay close attention. If you have 2 points in a space, and you can connect them with a path, the space is said to be path connected. Okay, there you go. Hey, in your defense, we have given technical definitions to words such as simple, right? A solvable group is actually something rather complicated. Anyway, that we have not defined. as I mentioned, a matrix group is topologically closed. And here's the definition. The n-dimensional torus, which is an example of a tori, is the group U1 cross U1 cross U1 cross U1 cross U1 cross U1, cross U1. So it's n-fold Cartesian product of the unitary, unimodular group, the unit circle, if you like. And there are a couple different ways to look at that. Neither of these really matter to us because I'm skipping the proofs, but I mentioned them out of interest. One way you can represent the n torus is just as diagonal matrices in GLN. You just take e to the I theta down the diagonal, and each one of those gives you a U1, essentially. So there's an obvious isomorphism between this and that, which is just strip off, like just, I mean, the isomorphism between this group and that group is literally cross out the diagonal. That's the isomorphism. Sorry, it seemed funnier to me. But anyway, another way you can look at it is you can also talk about a basis for Rn and define the integer linear combinations of the basis. That would give you what I would call as a lattice. It's a discrete grid of points throughout n-dimensional space. And if you take Rn additively and you quotient by that discrete lattice, then that gives you something which is yet another model, if you will, for the n torus. If you were to take Rn and mod by a k-dimensional lattice, sublattice, if you will, then that gives you the k torus across a copy of Rn of less dimension. Oh, I slipped past here something. By the way, SL2 that we talked about last time is not compact, as we'll see here shortly. And well, at the moment, it also is not the case that the matrix exponential is surjective onto this. It's not surjective on all matrix groups, but it is on the four I started with. It takes the better part of chapter 9 in TAP to prove that. Oh no, have I been doing what I think I've been doing? Yep. Ah, I hate it when that happens. Oh well, sorry internet. Everyone who matters is here, I guess. Ooh, wait a minute. I'm going to get comments. All right. Anyway, if you ask me nicely, I'll post the notes. All right, moving on. Theorem. Any compact abelian path-connected matrix group is isomorphic to a torus. What does compact mean? Compact just means that it doesn't go on and on. It can be bounded by some ball in the space. And so there's a notion of, you know, how far a matrix is from the origin in matrix space. It's just given by the square root of the sum of the squares of the components of the matrix. That's, you know, just what you kind of expect. Anyway, the proof is just this. If the exponential is surjective and the kernel of the exponential is given by, let's see here. Oh, this is just a sketch. I shouldn't try to explain it. So you can prove that the exponential is surjective. You can prove that the kernel of the exponential for a compact abelian path-connected matrix group is the integer linear span of those k things. And if you look at the first isomorphism theorem, since this is, you know, you have a exponential is a homomorphism, and this is its kernel, then that must be isomorphic to the image. But the thing is, the exponential is also a continuous map, and let's see here. Well, the exponential is a mapping to the group if it's surjective, and if the group is compact, you can't have G equals to this. Like, the thing is, this is very much not compact. Like, any copy of the reals is very much not bounded, okay? So if you had this non-trivially, then that would not be compact. So since it's compact, this must be gone, which means n is equal to k. But if n is equal to k, we've just got the n torus, which is to say that the torus is as big as the dimension of the group. In other words, that the group is a torus. So anyway, if you want to see the details and really understand, I'll let you look at TAP. So definition: if you have a matrix group, you can talk about what's called the maximal torus. So the maximal torus is a subgroup of the group which is isomorphic to a torus. And if it's maximal, that means that you can't find a larger torus, which larger dimension torus, of course, in which the given torus fits. So it's a maximal torus. In fact, you can calculate the maximal tori of our examples, and they're just this. The maximal torus of SO2M is diagonal matrices where you've got these. So what that notation means, guys, it's just the thing we've already written today. R theta is cosine theta minus sine theta, sine theta, cosine theta, it's that, okay? The 2 by 2 rotation matrix. So it's a diagonal with 2 by 2 rotation matrices. For SO odd order, you've got 2 by 2 rotation matrices down the diagonal and a 1. For UN, it's exponentials, complex exponential, imaginary exponentials on the diagonal. Likewise for SPN. And then interestingly, SUN has imaginary exponentials n minus 1, and then the nth one is based on the first n minus 1, right? It turns out when you study the condition that the determinant, well, there's an identity. The determinant of the exponential of a matrix is actually the exponential of the trace of that matrix. So if you have determinant equal to 1, what's that say about the trace? It says the trace must be 0. So when you study special linear groups, you find that the algebras must be traceless, must have 0 trace. So you can kind of understand why this has to be there if you think about this needing to be, well, there's a little bit of daylight between that idea and that idea. But the proof is a little bit technical. I just want us to have that. And there's a proposition, if we have any of our favorite matrix groups, and if we have T as the standard maximal torus, like I just listed up there, then any element of G which commutes with the whole torus must lie inside the torus. Right. In particular, T is a maximal abelian subgroup of G. This ends up meaning that we can calculate the center of these matrix groups rather easily. Like the center of SO2M turns out to be plus or minus identity. The center of SO odd order is the identity. The center of unitary matrices is just e to the I theta times I. In other words, that's basically isomorphic to U1. The center of the symplectic is plus or minus I. The center of SUN is actually isomorphic to Z mod n. So with this in hand, we can now argue, before I even show you anything else, we can already dismiss my question, is SU, by the way, SU2 has the same, has curses. Words. Where was I? SU2 would be has a center which is isomorphic to Z2. SO3, on the other hand, has a center which is isomorphic to I. I meant to look at SU. Did I look at SU2? Yeah, I'm sorry. I don't remember imposing the. I think I needed to impose the determinant condition to actually get to the skew Hermitian. I may have missed a detail there. See you, Stephen. All right. So I wanted to show you just a little bit. You can actually calculate the center of these groups using the maximal torus. It's really it's a simple calculation, actually. So because the maximal torus has to contain the center of the group, that means everything in the center of the group is in the torus. And so that means that you can take any matrix you like from the group, in this case, this one, and it has to commute with things in the maximal torus. And when you work that out, for this, for UN, you get that lambda 1 equals to lambda 2. But you can do the same argument for any two pairs of lambdas. So that gets you equality of all of the angles in the maximal torus element, which shows you that if it's in the center, it has to be e to the I theta. There's an identity missing here. It's just like that, as we claimed. Likewise, if you want to look at the center of SUN, well, that's actually the center of UN intersect with this with SUN, which means that we're looking for things of this form, which also have determinant 1. Well, the determinant of this is e to the ni theta, and if that's 1, that means if we put omega equal to e to the I theta, then we have the condition omega to the n equals to 1. And so a typical thing in the center of SUN is g equals omega I with omega to the n equals to 1, which is isomorphic to Zn by the kind of obvious isomorphism. So in contrast, you can calculate the center of SO3. Here's the actual details, and you can get by a similar calculation that the center of SO3 is just the identity matrix. So they have different centers. They're not isomorphic. And finally, because we all need to start our weekend, last two theorems. The beauty of the maximal torus, among other things, is if you have anything in the matrix group, you can actually reach any element of the matrix group by conjugating the maximal torus. The maximal torus reaches everything in the matrix group. Everything can be represented by conjugation of a maximal torus element. And finally, theorem 9.13, the standard maximal torus of G. Every element of G is contained. I think I already said that. What's this one? Oh, this one says that if you take the maximal torus and you conjugate it, you get another maximal torus. So they're not unique, but if you take the standard one and you... Now, finally, part of the reason I talk about all this is you can actually look at this and think about it and understand that all SOM is just rotations in orthogonal planes. The standard maximal torus for SO3 looks like what? Cosine theta minus sine theta, cosine theta, 1. Does that look familiar? It should. We had a homework problem in linear algebra where I tried to guide you into learning that you can choose a system of coordinates where any rotation, any SO3 matrix looks like that. What I was doing was making you find the element of the maximal torus which your orthogonal transformation conjugates to. That story generalizes to SO any odd order. So anyway, there's much more in this book. I would encourage you to read it if you're interested. Anyway, have a good weekend. And yes, I owe you 2 homework problems.